So I think, there should be some time at the end to chat, but if people have questions in between, it's fine. Just Gene, maybe you could monitor because I can't really see. Well, I guess I could. Can I do
Yeah,
that?
I'll do that. No problem.
Yeah, I can't really see everybody. So, okay. So, all right. So I'm going to talk a little bit about the sample design, which I think a lot of people, maybe not everybody, are familiar with. So a little bit of background on that, and then I'm going to get into sort of the mechanics of how you would analyze this with some existing software, and as well as just sort of a bit of the underlying intuition, if you will, about why you need to use specialized software, as well as why we're seeing some of the results that we see. So hopefully this will be worthwhile. It's in some sense, I'm going to try to cover in 30 minutes what could be a whole course. So if not all of it follows or makes sense, that's just the way it is, I guess. And I also do use a few equations, so you'll have to just sort of bear with um, uh, the way that PowerPoint's decided to show this. Okay, so birth certificate is a sampling frame. So this is not a unique idea, although it's not terribly common. And at least I was introduced to it through Nigel. And I think the way we're using it here is, if not unique, pretty close. So, but very cool also. So the idea is basically, right, all birth certificates in the state include both the location of the birth and the attending physician if there was one. Um, so about 99% of births are in the hospital. You look at the birth certificate data, you see the exciting I-75 at exit 210. Somebody didn't make it, right? As well as, more traditional home births. But the vast majority are at a hospital. And 98% of the Lower Peninsula births were one of the 95. And this is now perhaps somewhat outdated data. This would have been like in 2012, 2013. There were 95 birthing hospitals. And so the idea is that we can use birth certificates to construct a sampling frame consisting of clusters of birth grouped together by hospital and provider. And if we sample hospital proportional size, and size being the number of births that occur at a hospital and relative to other hospitals at a given period of time, we basically get approximately equal probabilities of selection. So again, I don't want to spend too much time on the math here, but basically, if we sort of think of S as sort of the set of all births that happen in at least Lower Peninsula births and the birthing hospitals, which is basically pretty close to just births in Michigan, um, then the probability of an individual birth being sampled is the probability of that hospital that they're giving birth in being sampled times the probability of an individual birth in that hospital, individual birth being sampled, given that the birth was in the hospital. And so, through the magic of multiplication and cancellation, we can see that the probability of a hospital being sampled is basically this M sub alpha, which is the measure of size, the number of births, divided by the total number of births, and then times the number of hospitals that we sample. And then we multiply that by the number of births that we sample at the given hospital. But then that's out of all the M sub A births that occur in that hospital. So coolly, we get this little cancellation here between the M sub A and the M sub alpha in the numerator and the M sub alpha in the denominator. And so we're left with something here that doesn't involve anything other than a constant. Basically, A times B. So that's the total number of people that are going to be sampled or births that are going to be sampled. A hospitals, B births, and sampling a constant number of births in each hospital. And then divided by the total number of births, which is we're going to call capital N. So the trick is there's two things that happen. One is that you get this equal probability of selection, which is very nice. And secondly, by sampling the same number of births in each hospital, you can kind of control the costs, right? So as we go out, we go in a hospital, we sort of have a team, if you will, goes out, and whether the hospital has thousands, hundreds of births or thousands, we try to get the same number out of there. So it kind of becomes you get efficiency and both statistically and logistically. Okay. So what did we do? So based on some sort of guesstimates of available resources and costs, we decided to sample 10 hospitals. We thought that was kind of the maximum that we could manage, and then sample 100 births per hospital. We also did something called stratification. I'm not going to get too much into this. It's just sort of I'm not trying to formally use this in any way, although it does, I think, have some benefit. We stratified based on quintiles of Black deliveries, right? So that's information we can get from the birth certificate database. It implicitly stratified on urban, rural, and to some lesser extent on socioeconomic status. So that meant that we were sure that when we went in and pulled our sample that there wouldn't be sort of chance, even though it's a probability sample. So in expectation, everything is going to be balanced. It means that we can actually be sure that we have reasonable balance on that particular sample. So okay, and so we use birth certificate data from the little over 215,000 births in 2012 and 2013 to kind of compute our measures of size. And then in sampled our hospitals. Now, recruitment actually takes place at the provider clinics. So once a hospital is sampled, our attending physicians were grouped into provider clinics, and the second stage of the PPS sampling was undertaken to get 2 practices per hospital and sort of 50 sample per clinic. We also threw in Hurley Hospital at Flint with certainty, so we just didn't show up in the sample, but we wanted it in there anyway, in particular because of the lead crisis that was going on at the time. And so that gives us a total sample, a target sample of 1,100. And so just to kind of show that we got some geographic dispersion and that it kind of, fit the population distribution, right? And so if you're sampling at random across births, you'd still want to see more births where there are more children. Children tend to be where there are people in general. So we got Traverse City and sort of Port Huron and kind of more rural areas. We picked up the very large hospital delivery system out in Grand Rapids, as well as Saginaw, and then 6 hospitals in sort of the either Detroit or surrounding areas. And then the blue dot, it's just for Flint because it's not part of the probability sample, though it's part of the March sample. Okay, so, sorry, there was right. So everybody here probably knows a little bit about Michigan, so you know that where people tend to live and where they tend not to in the state. Okay, so any questions about the sample design? Sorry, I just got out of class, so I'm treating you like my class. Again, if I don't hear, I'll just plow along here. Okay, so recruitment. Um, so clinic personnel required to introduce the study to patients. If they were interested, the researcher proceeded with a consent process. There was some variability in enthusiasm amongst the clinic staff, which affected response rates. All women were recruited at the first prenatal visit. And to avoid oversampling women who are switching providers, we drop and replace those who leave the sample clinic before birth. Data collection itself, we tried to get prenatal visits at the first, second, and third trimesters. If they came in late, then we just didn't do those prenatal studies, but we still recruited them we didn't do those data collection at those trimester visits, but we still recruited them to the study. So it generally consisted of phone and online surveys. Biological specimens were generally collected at the clinic, coordinated with routine clinical care. We tried to get the placenta at childbirth. And then post-natally, we got phone and online surveys, 3 months, 9 months, 2 years, and annually thereafter with an in-child person assessment between ages 4 and 5. Now in March, I think there may have only been, I don't know, certainly less than 10 of those at the time that the March 1 ended, but they were sort of continuing into March 2, so hopefully we'll get more of those. And then we also have self-collected biological specimens. So, this is all somewhat ancillary to all critical for the actual science, but somewhat ancillary to what I'm talking about today. Okay, so response rate, amazingly, I think all 10 hospitals we sampled were recruited. So huge kudos to everybody if anybody's on the study that was involved in that part of it, who's on today. We did have one that closed and we had to replace, but that doesn't really count against the response rate. Um, and the majority of the clinics we approached also were agreed to participate. Um, Most of those they refused. We were able to replace them with another clinic. There were two hospitals where we gave up and just used a single clinic to get the full complement of births. So in the end, we got a little over 1,100, mostly due to multiple to twins. Um, so we wanted to recruit 1,100 women, and we certainly got that. And they gave birth. Now the time period is pretty long. In that too much here, but you might remember something called COVID that happened. That probably we were already well off schedule when that happened, although on track to probably finish within 4 years, but it stretched out to more like 6, I guess, in the end. So, um, okay, and so in terms of the response rate, so at the hospital and clinic level, which I think honestly is probably the most critical thing for non-response bias, we did very well. Within the clinics, it's a little hard to say how we did because recruitment kind of occurred at the convenience of the clinic. We know there are at least 306 women that we approached that refused to participate, and they filled out a little questionnaire about why that was. And we got a third stage response rate then, if you sort of treat that as an upper bound of about 80%. So putting that all together, we can see this yields a response rate of about a little over 50%, which anybody who works in the survey world nowadays, that's just fantastic. So for just about any kind of general, in this case, somewhat constricted, but still general population study. So particularly one that's so difficult to kind of deal with given time constraints and everything else, right? So, nonetheless, we in theory the sample design meant that each birth had to have an equal chance of being recruited, but there were the two eventualities that prevent this from happening. One is we used this proportion of births in 2012 to 2013, but our actual recruitment really stretched out over a long time into the future. So the actual proportion of births in the hospital doesn't necessarily match the proportion that we did initially. So if we assume that there's some overall proportion of births that come from, say, University of Michigan Hospital, which was one of the sample hospitals, but it turns out that in practice, it may be the actual proportion out of the sample is now twice that what we found initially. It's a bit of exaggeration, but it's a little bit the direction it happened. So we kind of want to weight down by 1/2 those women from the University of Michigan. And conversely, if there are some hospitals, I'm sorry, we'd want to double the weights of the women from the University of Michigan. Conversely, if there are some hospitals where they shrank over the time period, then we want to weight them down. So um, so that's one issue. And then the second issue, of course, is that not all the recruited women responded. We already saw that, right? So that could affect that. So the first one is sort of easy to deal with, a little weighting correction. Basically, um, you put a weight that's proportional to the uh, uh, change in the birth rates at each hospital. So proportion of the proportions, if you will, with a little constant that's then kind of designed so that the number of weights, the sum of the weights adds up to the total number of Lower Peninsula Michigan births minus the births during that time in Hurley, which is our Flint hospital. For the Flint hospital, we did a first stage weight that just looked to match the weighted fraction of the sample Hurley births, the proportion of Hurley births in the population. So then the weighted sum across all of these then equals a little under 600,000, which is the total number of Lower Peninsula births between December 2017 and August 2023. So then we had a second stage weight that used what's termed calibration or waking rates. And this can adjust for non-response as well as simple sampling error, right? So we went out, we got 1,000 women. It's a fair number of women, but still, relative to the whole population, there still could be some imbalance even by chance, right? And then on top of that, if certain types of women were more likely to respond positively to our invitation to join the study, then both of those can sort of induce bias. Well, that the second one induces bias. The second one, the first point, is sort of a reduction in variability. So this thing called raking or additive proportional fitting, I'm not going to get into it, basically uses the known marginal distribution of the selected variables to develop weights. So the weighted marginal distributions of these variables matches the population marginal distribution. And I use this, I guess IPF refers to interval additive proportional fitting, and it uses the hospital weighted data, so the design weight information, this sort of adjustment at the first stage is retained. And so what data did we use from the mother? We had their age, race and ethnicity, education, marital status, gestational age, reported smoking behavior, reported alcohol behavior, and gestational diabetes. And then from the child, we had the sex, birth weight, and APGAR score. So, okay, so basically the results here, it's a little small, but hopefully people can follow it. I'll to just go over the first column here is basically ignoring any weights. The second column is just using those selection weights, those first stage weights. And then the third column is using the raking weights. And by definition, they match the population distribution because that's what raking does. So this isn't like some magic here. Well, there's a bit of math magic, but there's no immediate fix there. But the real thing, I think, is to kind of compare the selection weights with the fully weighted / population distribution. And generally things look pretty good. I'll just run through this. There are sort of three that maybe were a little bit off. So in particular, we kind of a little, I don't know, for some reason, sorry, this looked better on my original slides. We tended to oversample a little bit the Black population and undersample Hispanic population. And smoking behavior was really a little dramatically different. We had twice the number of women reported smoking. I mean, the birth in this, I won't get into details. This is largely the birth certificate data for both, right? Both the population and the sample. There's some issues there were a few women we didn't have birth certificate data on. We filled in from the um, from from the March study, or in a few cases even imputed. But the smoking rate in our sample was about twice that in the population. But most of the stuff's actually pretty close, and even the ones that are off are not that far off. So generally, so you can see the gender distribution is pretty close.
There's a typo there in the low birth weight.
There is a typo there. This
Oh,
should be 8.5. Sorry, not 1.5. So yeah, so 9 versus 8.5. Age distributions, maybe slightly older, I think, in our sample, but not too much. Education, again, you might expect this. Slightly more educated, not huge differences. Slightly less likely to be married. And in terms of the birth outcomes, very close, actually, I think on, sorry about the typos here. Should be 0.6. But uh, very close in terms of gestational age, APGAR scores, gestational diabetes, and that kind of thing. Um, so I think it's evidence that we sort of did what we set out to do, which is to get a reasonably representative sample of Michigan births. Okay. So okay, so we want to there's account for the sample design here. So the sort of standard called Stat 101 approaches for analyzing data typically do not account for weights or the multi-stage sampling of the hospitals or than the sampling of the individuals. So the weights, again, even though there's not huge differences, I do think there is some value in trying to incorporate these if possible, because we're essentially sort of counting those that had lower chances of being selected or included in the end, whether it was due to changes in where the hospital births were or due to some non-response. Um, And so that can impact both the point estimation and the variance estimation. And then uh, for the clustering, women who give birth at a given hospital will be more alike than women who give birth at a different hospital. And so that actually impacts the variance estimation in a way I'll talk about here in a second. So weighted estimators, right? So they replace unweighted sums and statistics with weighted sums. So if you're looking at a mean, rather than just summing up all the data in the sample and dividing by the sample size, you sum up the product of the weights and the variable and divide it by the sum of the weights. So a simple regression of y on x. Again, depending on how far you got into your remember your basic thing here. It looks something like n times this covariance divided by uh, the means um, over the essentially the variance of the x's, which can be written as a sum of the x squares minus the square of the mean differences. So basically, if you turn all those into totals, you then just replace them with the weighted totals. So rather than just looking at the product of x and y, you look at the product of x, y, and w, multiply all three of those together and take their sum. So that's how you get a weighted estimator of the variance. If you look at it, if you've gotten into like matrix algebra, basically you sort of stick a diagonal matrix of weights in certain places where you're multiplying the design variables. So it also impacts variance depending on the association between the weight and the outcome. So in particular, for the mean, the variance gets inflated by 1 plus this coefficient of variation over the simple random sample assumption if there's no association. If there's a stronger association, there's less inflation or even deflation. We'll actually see that in an example. You get improved efficiency. In March, this coefficient of variation of the weights that's basically defined as the mean of the weights squared divided by their variance, so the square of their standard deviation, just about 1.76. So kind of the worst case scenario, um, you get a reduction of about a factor of about 2.7 in terms of the sample size, but we'll see that that's, again, not typically going to be the case. Um, Something else that maybe people are a little less familiar with is this accounting for the clustering. Now, this generally increases variance because it's a function of how similar subjects are within a cluster relative to the whole population, sort of this intra-cluster correlation or rho. So in the simplest case, we'll assume A clusters to be observations per cluster, or you can think about it maybe as the mean number of observations. It varies a little bit as we have here. So variance gets inflated by this 1 plus rho times b minus 1. So if rho is 0, basically there's independence within clusters. So you can sort of think about the sort of clusters now, the little membrane around them basically just disappears. And now you're just sort of sampling from the population. It's the same variance. Worst case scenario, if they're all identical within a cluster, right, then your variance gets inflated by a factor of b. And so the effective sample size just becomes the number of clusters, which you can imagine, right? So if we had some crazy variable that for some reason like was identical for all women in a given hospital in each hospital, essentially our sample is basically just the 10 hospitals now, right? That's the only place where there's variance to understand. So that variability is based on those 10 hospitals. So so for March, B is about 103. So 1130 divided by 11. So rho of 0.01 doubles variance, 0.02 would triple variance, and so on and so forth. Unfortunately, most of the in-hospital correlations are very small. So we don't expect a lot of, either much closer usually to 0 than to, anything like 1. So some of our key, so okay, so then we want to talk about how we actually analyze this. So the key variables in the data set, and I'm Not sure if, um, let's see, just looking to see who's on here. Okay, Caitlin is on here. So Caitlin can correct me, but these are the variable names that I sent her. So, so the weight is the so-called final weight, which should be used for the analysis. And the cluster, sorry, this should be is, not in. Cluster is hospital. Now, most statistical packages have specialized components that deal with complex sample design. Excel does not. So if you're doing your analysis in Excel, then you're not going to have to move on from that. Um, in R, which is sort of come the default nowadays among statisticians, I think, these biostatisticians, there's a survey package that can handle a lot of this. SAS, the ProcServe procedures, Stata, the SVY procedures, and SPSS. Again, I'm not sure what people use, but it's more of the social science world. The complex samples modules. I haven't used SBS in 30 years, so I won't talk about that. Stata I do use on occasions. It's been a little while, but they actually have very good survey procedures. SAS is a little bit behind the curve, but they have a lot of the basic stuff covered now. And R is well, it's R. It does a lot of stuff if you know what you're doing. Okay, so I'm just going to look at a little example. It's maybe kind of a toy example. Marijuana use by mothers. And so I think I don't know if you want to give a shout out to Bon, but this is the data that she's pulled together. Um, but basically, mothers are coded as using marijuana if they either self-reported use or cannabinoids were detected in their urine. We dropped about 1,500 women from the analysis. I should say 1,500 births, not women, are excluded from the analysis due to self-reporting urinalysis data. 1,100 and well, 1,150 available for analysis. I think in this case, all of the women here were singleton births. So, but this is a nice point. I think to note the design is focused on births, not mothers. There are 25 twins in the samples, and so there we have 1,105 mothers, 25 twin births. So I guess 50 twins. Um, so we can either focus on the analysis on births, right? So children proportion born to mothers using marijuana, et cetera, or use the child weights in lieu of the mother weights if you want to do a mother level analysis. I think the former is preferred, but the latter won't be off by too much. So I'm going to try to do that here.
And Mike, we can give a little shout out to Bon before you move on because she's on the call for one thing. So
Yay.
Bon Al Sahab, she did a formal postdoc with Echo with us, and she also wrote for several smaller grants and got additional funding to be able to do this urinalysis. And so she's working with your sampling weights now to
Yep.
produce what will probably be our first published March paper using the sampling weights. So thank you, Bon. We're super excited about this.
Okay.
And
Thank you.
Bon's
Okay.
on faculty now at MSU, but in the Department of Family Medicine. Is that right, Bon?
Okay.
Yes, that's correct.
Fine, you can say if I've got this correct here. I think this is what we sort of settled on most recently. But the estimated proportion of children to mothers born to mothers using cannabis, ignoring the sample design, was about just under one fourth. But
Yep.
when we count for the sample design, the estimation is considerably lower, about 17%. Still maybe higher than one might have expected. So the R code on this, so I should say if you use R, then this is describing how to use the survey package. If you don't, I have some code in SAS. If you have something else, well, you're on your own for now, although some things I can probably help with. But the R code sort of starts, you have to just, it likes having this data in a frame. So you have to create a data frame. And it's where the mean, basically, I just need my two design variables, my weight, my cluster variable, and then the outcome, the Y, if you will. And then I then, let's see, why is this not working? Sorry. All right, so then I have this design, uh, SVY design, basically tells, I have to tell it where the data is, what the data file, what the data frame is. This IDS means essentially the clusters, which is the hospital here, and the weights, the weight variable. And then, why did this fail? Okay. Um, Somehow on Zoom, it's not working the same way it did when I did it on my computer. But anyway, here we are. Okay, so then the last piece here is this SVY mean. So it needs a little tilde sign. So it's kind of like it's a bit weird. This, for those of you that use R, this is sort of typically what you use for the independent, the thing that connects the independent variable with the dependent variable. But for whatever reason, there's kind of a null independent variable, and your dependent variable here, or your mean, that your variable you want the mean of is here. You have to tell it where to find this design object that use the SVY design. And I just wanted to keep to just, rather than having to tell me, oh, there's missing data, I can't do anything. It's just going to throw out the 15 births that don't have cannabis use on there. So okay, so then the outcome, it spits out down here. You can see the predicted um, distribution. And then I'll come back to this in a minute. I actually use this confit function because my degrees of freedom is going to be different when I count for the sample design. So so I need to tell it what the degrees of freedom were. Um, and So when I tell that, then it spits back a confidence interval, right? So that's how I got this up here. Okay, so SAS code, some sense a little easier. So I just have to tell it proc survey means. I have to give it this cluster variable and this weight variable, and then the variable that I actually want the mean of. Okay, so the design effect. This is again sort of a little bit of stuff more in the series sampling world, but it kind of gives us the ratio of, it's a way of sort of understanding the impact of the design on variance. And it's the ratio of the variance of estimating as assuming a simple random sample versus the variance of an estimator that accounts for the design. So it's kind of easy to compute here because I know the variance of a proportion is just going to be the proportion times the estimated proportion times 1 minus that estimated proportion divided by the sample size. So in this case, it's whatever it is here. And the variance of this I can just get from my standard error, squaring my standard error here. Let me get that. So my design effect is actually 0.65. So equivalently, it means I have an effective random sample size is actually bigger than my sample size. It's like 722 instead of 1115. So this is kind of an example of super efficiency. Maybe due to this unintentional oversampling of tobacco smokers who also have higher rates of marijuana use. As I mentioned before, if the weights are sort of highly associated with the outcome, you can actually get more efficient estimators. And so in addition to like adjusting for bias, it also kind of increases efficiency. So I wouldn't expect these to hold for all estimates in March. And indeed, in this example, they won't. So just to do a second example using the same outcome, very simplistic, just a logistic regression of marijuana use by mother's education. And here I just use 4 categories. So less than high school, some college, and college graduate. My R code. All right, so basically, I guess, so I'm using the SVY GLM now. So now I have a regression model. So, my outcome, I'm going to use education as a factor. I just a binomial, right? It's a 0, 1 outcome, and I have to tell it my design. So you can kind of ignore this warning message, the non-integer number of successes whenever you use weights. That's typically going to happen, if the weights have decimals in them. Um, so that's fine. I don't care about that. Okay, so then I get my object and I just take the summary of it here. So I've recoded education. So level one is college, level two is some college, not a college graduate. Level three is high school, and level four is less than high school. Um, so again, I can use my design this confidence int, I guess, function to get the confidence intervals associated with it. So these are all in the log odd scale, so I compute them to odds ratios. I get some pretty big odds ratios, although there's a lot of variability in there. Um, I did look and see. I can show the table. I didn't show it here. There is the um, reported or the reported combined with actual cannabis workers for women with college educations is very low, and then it's again around um, closer to 20% for the rest of the group, and you can see the associated um, odds ratios. So if I treat it as a simple random sample, it even gets stronger, as you might guess from the fact that the overall rate was diminished somewhat when I put in the weights, and the credible intervals are less narrow. And in particular, if I want to compute the design effects, now I have design effects that are greater than one, right? So effectively, an effective sample size that now maybe be in the upper three digits or the very low four digits for these effects. Still significant. SAS code, pretty much the same. I just use survey logistic now. If I want to use education and get as a categorical variable, I have to use the class function, the same clustering and weights. Okay. So a little bit about this degrees of freedom issue, right? So you might remember when you have a small sample size, you have to count for the degrees of freedom available to estimate the variance and construct confidence intervals. So for the mean, that's sort of n minus one. So for a t statistic, that means you multiply the standard error by um, uh, a t t point 9.75 at 29 degrees of freedom gives you 2.05 instead of 1.96. So here we have 1130. So maybe the t statistic you multiply by 1.962 instead of 1.960. Wrong. So that would be if you had a simple random sample. So for cluster designs, for the mean, you have a minus 1 degrees of freedom to estimate a mean. So that's 9, right? 10 minus 1. So essentially, we're using 2.262 instead of 1.960 to compute confidence intervals. Not a huge impact, but enough that it's worth accounting for, right? So if I just used my usual Z statistic, then I would get a confidence interval from 0.152 to 0.192. But then if I use the correct um, uh, degrees of freedom, I get 0.49 to, sorry, 0.149 to 0.195. So the interval's about 6/1000th of wider, 6.6% wider. So the situation gets worse for regression models where the degrees of freedom now becomes a minus p minus 1, where p is the number of predictors in the model. So in the logistic regression example, I actually only had 6 degrees of freedom. So I've created an alternative cluster variable that separates the hospitals into two subsets at random. It's called pseudo hospital. You can use this instead of hospital. It allows for regression models of up to 15 predictors. It's somewhat anti-conservative in the sense that it might overestimate the precision of the variance estimates, but maybe not by much, and in practice, maybe not at all. But it does properly account for the overall hospital clustering. So in some sense, this is a somewhat conservative way of estimating degrees of freedom. So taking this back a little bit is probably not too bad. All right. So that's basically where am I at here time-wise?
Wow, Mike, before we open up for questions, maybe give you a big virtual round of applause.
Oh, thank you.
Thank you so much. Thanks for presenting this to us, and thanks for getting to this point because we work on this cohort. It's like a never-ending project, but
Right.
we have to celebrate
Right.
the
And
milestones
I
as
do
we
think I would
go.
add, I didn't say here about next steps. I think there is one more next step, which is we might want to try to develop some weights because we're not always getting women are responding or not, right? At each one of for each one of these
Mm.
waves of data collection. So if not for all, at least for maybe some of the key ones, we might want to do some, at least look into some. We don't necessarily have to create them, but at least look and see if there are some significant differences between the women who responded and those who didn't at different points and think about that as well. But at least for this first cut, we got it.
Excellent. And you're about to publish a paper describing this, right? And you
Yes,
also have created a sort of instruction sheet that we will include with
right.
our
So a
data.
lot of what I just discussed here is in that instruction sheet. The instruction sheet has some other stuff and more background as well, basically, but the core stuff is pretty much here.
Excellent. Well, thanks so much, Mike. And I see some people turning their cameras on. So who would like to start the discussion? Bob? Glenn? I see you're looking for your mute.
No, I didn't have a question. I'm just like you. I'm very glad to see this point. Obviously, there are very few people who could have done this, and thank you so much, Mike, for doing
Well,
this.
I don't think the former is true, but you're welcome.
No, no, as I wrote you, Mike, this sampling stuff was somewhat above my statistical pay grade.
Yeah.
It's so exciting. I mean, we are at such an exciting point right now.
And I think I mean one bigger takeaway is all I did is stuff with the discussion of the weights and the clustering and so forth, particularly the weights. I mean, we're pretty good where we start, you know.
Yeah.
A little bit of the difference there is the Flint's a little oversampled, right, and so forth. But we did pretty good. The weights are kind of almost a second order correction.
It's really amazing. And I know some people were skeptical going in, so it is
Yeah,
amazing how well it did. I do have one question for you, Mike. I often think of a probability, so this is a probability-based sample, right? And I often
right,
think of that as not having equal chance, each participant not having
right,
equal chances, but having a known
right.
chance. But you actually mentioned that theoretically, the women at these hospitals have about an equal chance. Is that just a characteristic of our design because we had
Yes,
the
that's a characteristic of our design.
gotcha?
It didn't work out quite that way, but we can hopefully come up with the what we're essentially treating as a known probability selection, right? Which is this inverse of the weight. So if you take all of our weights and you divide them by one, that comes like a well, and multiply them by by the sample size. I think that becomes essentially the probabilities, the observed sample size. That's like probability selection, more or less.
And then what that allows us to do, right, with these weights is to generalize to
Yeah,
the population of the state of Michigan, right? So
right,
that's why this is
exactly.
so exciting.
Yep.
Excellent. And I see that Bon has asked if you will share your slides, and I know we're going to put the recording online, but would you
Yeah,
also
no, I can send them along. I
share
might fix up a couple of typos, but yeah.
Excellent. Thank you. And then Rebecca has her hand up.
Yeah, hi. Sorry, my video isn't working on this computer. But I had a question as to how one would update this for some of the ancillary studies that might only be recruiting from a subset of the overall sites. Like, can you do some kind of double weighting to
Mm,
correct for that?
well, yeah, that would be that might depend. I think that would be obviously somewhat study specific. Conceivably, you could try and develop weights that look at differences between that hospital and the rest of the sample. It's no longer, it sort of loses the guarantees that you have from this.
Yeah, of course.
Alternatively, you might just sort of look to see how does this differ. And again, from the rest of the sample, and if it doesn't differ much, maybe it's not worth worrying about.
It's a good question, Rebecca. I wonder when you're doing your analyses, maybe you want to consult with Mike just to double check some.
Yeah, I was
And
going to
depending on how
say
you're
Mike might
slicing it,
want to
if there
look
are
out
things that
for
if
some
there's sort of
detail.
subsets of the population that are sort of taken from the whole population, you can just use the weights and everything as it is, right? So if you're looking at like diagnosis of autism or asthma or something like that, don't worry about it. Just use it. It should be representative of that group.
Yeah, for
If
my
you're
study
looking
in
at some data
particular, we
collection that was only
didn't.
done in like Hurley, that's a different matter.
Right. So it wasn't quite like that, but we didn't include, say, the Traverse City folks. We have actually reached out to more recently, but they have to travel down to be in our extra studies. So we're not expecting people who are,
Yeah.
really far from the Detroit area to have high success rates. So I'm kind of thinking about
Right.
how we
So you
could.
could do some weighting there, or maybe just restrict it to the 6 hospitals in the southeast.
Yeah.
Yeah. But then I probably would not use the weights. I would just use the 6 hospitals,
Yeah. Yeah.
unless you want to develop your own, set of weights for those.
Great. Well, you'll probably hear more from me about that in the next couple of months.
That's exciting, Rebecca. It's all moving forward. It's
It
great.
is.
Other questions or comments for Mike?
This is Tim Fei. So Mike, I wonder, since we use these weights, can we still like consider the hospital as a like random effect?
Right. So, I mean, I'm using the hospital here, and these survey statistic approaches and the survey packages don't treat the hospital as a random effect per se. It's sort of a different way of incorporating it. Um, if you did want to use it as a random effect, that's with 10, you could probably get away with it. I don't think R has it. I think there's some very specialized packages that allow you um, to develop to account for that in a random effect. And there'd be a little extra twist because you basically would need to have the first and second stage sampling probabilities. And so that would probably, like the second stage one, I would probably just take as the difference between the selection weight, which I haven't provided actually, and the final weight. So that might require a little more work, and I think it's restricted. Like M Plus does it, and some of the folks out of Britain have some software that does it. I can't remember the name of it. Um, there are some things that fit weighted random effects models, but I think R and SAS do not.
I see. Thank you.
Nice to hear from you, Tang Fei.
Virgin?
Nice to hear from you, Tang Fei.
Oh, that's you see.
Any other questions or thoughts for Mike? Mike, when I did my dissertation, I used the NHANES data, and
Yeah.
then SAS didn't have a survey package back then, so you had to
No,
use
I know.
Sudan. Does
Sudan,
still
yes, I was
exist?
about to say Sudan, right? That's still out there. You can do an add-on.
Ah,
I don't know. Maybe Sudan does random effects models. I haven't looked at it in forever. Yeah, CARP, all the when I was also, I mean, that was back in the day, right? All this stuff was kind of R didn't exist. There were no SAS had nothing, SPSS had nothing. R and Stata didn't exist, so it's much harder to implement these things.
yeah, I was impressed that you showed most everything has a capability to do it now except for Excel.
You can do it in Excel, you have to do it by hand.
My gosh.
Compute all those things, which I didn't show you to do, but
Oh,
you
probably
would want to do anyway.
unnecessary. Well, this is exciting, and I guess, Mike, I'm hoping you'll be available for consult if people want to apply the weights, because at least the first dozen times we write papers using
Yeah,
weights, we'll
yeah.
need your help.
And I'm realizing I think I was also running out of time, but I could have a little discussion about use of weights in models at some point because it's not always, I mean,
Hmm.
it's not always clear that you want to use weights when you start doing regression modeling as opposed
Ah.
to like some, um, um, descriptive statistics, I guess, or analytic statistics. So where you pretty much always do.
Well,
So
you certainly could do a part two for us
yeah,
sometime if you like.
yeah.
And while we have people on the phone, do you have any questions for the the draft of the paper that is about done now?
No, I think we're going pretty good. I mean, take into consideration. I think Bob and Gwen, you had some good comments. Um, I think we just sort of think of how much we want to do, maybe some rewriting of the introduction. But otherwise, hopefully people, please, if you haven't had a chance to look at it yet and want to, and you're sort of on the list of people being bugged about it, then please do so.
And the target journal for that is American Journal of
Yeah,
Epidemiology.
so we are targeting an epic journal, not a clinical journal.
All right. Well, if there are no further questions, we will
Okay.
probably see you in a month.
Yes, and yeah, and I have my email here if anybody has stuff they want to bug me about later.
That's great. Thank you so much, Mike.
Thank you so much.
Thank you.
Thank
Thank
you.
you.
All right.
Take care,
Thanks
folks.
again. Bye-bye.
Bye.
Bye.